So before I introduce Giovanni, let's just go around the room and have everybody just say your name, you know, what brought you here and what you're working on, or if you're looking for a job or want to, basically have any announcements to make. So, Robert.
My name's Robert Quadra. I've worked with Joe when he started this. Just here to learn more about the good semantic stuff.
Susan Kelly, and I have general interest in Semantic Web and e-commerce, and I'm looking for work.
Ron Kell is also a co-organizer and focused on magenta development.
David Benjamin, I work for a local subsidiary of TripAdvisor, senior software engineer, and we're hiring in the Java.
Chris Anderson just moved here 2 months ago from Basel, Switzerland. I used to work with Novartis Pharmaceuticals. My interest is, in my past background, I worked in healthcare semantic interoperability and data standardization in clinical settings. And I'm looking for a job.
I'm Art Snitsky. I'm a software engineer and I work for a company called Red Prairie who developed a warehouse management system.
I am Dilesh Tiloda. I work at Train Citric Fox, the television group, develop Java and Oracle-based applications.
Raymond Gohanyan, I'm doing currently a Java consultancy.
My name's Alan. I'm a co-organizer at the SimTech at SimWeb, and I'm a co-founder of a startup called NetMinds.
I'm Kai. I'm a developer and I work at NetMinds.
I'm Beth, and I'm a co-founder at NetMinds.
If you want to work at NetMinds, hang out in this room.
Victor Archuleta. I work for a company that manages outpatient oncology treatment centers, and I'll be looking for a job at the end of November. So I met with Evelina and Carolyn last week, and they told me about this meetup, so showed up.
My name is Nico. I'm working on a startup. I'm interested in the semantics.
Parag, I work with Semantic, and I'm into web application development.
Okay. I'm Austin, and I'm a recruiter. Just kidding. I'm a developer. So I recruit other developers.
My name is Blake, and I do iOS development, and I'm interested in how that can interact with semantic web and stuff.
And your brother's a recruiter.
Yes. He recruited me first.
I'm CD. I do a little bit of Linux, a little bit of PHP, and struggling trying to get my own thing going. So if you know anybody, angel investors, I'd like to talk to you.
Hi, my name is Carl Mullins. I'm basically a software developer, but basically used to work with the aerospace and government. I had to move over because I actually didn't have to, but software, academics, and everything else in general all kind of merges together. So you got to keep up with it. So the best way to do this is keep going back to school, and so I just kind of keep myself busy.
I'm Michael Maljury from Morph Labs. We make an OpenStack private cloud. I'm interested in cool applications that run on cloud, like this one. And we're also looking for Python developers for OpenStack. So if anybody's interested, see me, please.
Yeah.
My name is Mike, IT independent consultant, and looking for new opportunity. And I'm interested in the stock for cloud-related purposes.
My name is Nihat. I'm a PHP developer. I'm working at Linux too. I'm working for internet brands here.
Carter, a recruiter here at Q.
Al, LA Trends Research and Investments.
The Q team, I'm Evelina, Nicole,
Joe,
and Callie.
do you guys want to come say a couple words, or
they have?
So yeah, thank you all for coming, and thanks to the organizers who are so very good at supporting the community here in LA, which is all we really want to do too. We try and differentiate ourselves by actually being a part of the resources and community that's here. So if you need help with the resume, finding work, come see us. Come talk to any one of us. We'll be happy to help you however we can. That's really it.
Which leads into the intro, which is I met Giovanni last year at SindiceTech. This is the biggest Semantic Web conference of the year, and I ran into him again this year. Sindice is what he had been working on for a long time, and it's really kick-ass, must-see. So I said, hey, you're going to be in LA, you got to speak. So we put it together really fast, and I'm going to let him go on here.
Well, thank you so much. Hello everybody, so my name is Giovanni Tummarello. I'm an Italian, but I work in Ireland. So most of the work that you see here is in Ireland, but also in Italy. So basically I have a part-time, a funny part-time, by which I go back and forth between Ireland and Italy every month, basically. So what we have been doing is, in Europe we've been pretty excited about semantic technology like Semantic Web since a long time. And when I mean excited, I guess also I mean funded. So we've been pretty lucky to have a very generous research program. That's something that has been funded by the EU. It's called the FRAME program. And I have to say, if you want to sum everything together, at least €500 million, which is several hundred. Probably $600-700 million went into semantic web research in the past maybe 10 years now, actually easily. So there have been a lot of things. Now you could say, oh, what has this brought, right? Well, there is a lot of competences, I would say, a lot of little projects, a lot of people tried, and I guess certain topics they just require some time to mature. Well, quite some time, as you can say. As you can see. I've been really driven by this dream of semantic web, of being able to exchange what we know on the web. The dream would be that of information offer meeting information demand automatically because of the structure, because of the annotation. I know something, you're looking for something, and thanks to semantic technologies, bam, we find each other on the web, right? Instead of you being searching. And that's really the dream. There is this institute called the DERI Institute, Digital Enterprise Research Institute. If you've been around a little bit semantic technology, you find a lot of DERI being mentioned here and there. And the tagline was making semantic web real. That's why in 2007 I joined the institute, and there, I started funding a team, created a little team. I was lucky also with funding. We raised a couple of millions, and we were able to build what you see here. A little bit of background. Even more on what I was doing before going to the DERI Institute. Well, I've been working on semantic technology, like I was telling you, maybe since 2002. And I found RDF, and I was really excited because it really looked like, hey, it's a graph, but it's also very simple, so you think you can do everything with it. So, and it's something that excites a lot of people. And it was the time of peer-to-peer. I remember 2002, something like that, Napster, or Emu, or whatever it was. And this idea that distributed, right? And also this idea of like harvesting and collecting and because you wanted to keep it for yourself. You never know what's going to happen tomorrow. The internet might collapse. We still didn't believe the internet was going to collapse or something. It was just too cool. Yeah, I guess it was just too cool to be true and say, well, I want to harvest as much stuff as possible because you never know. Right? So I built peer-to-peer systems for the semantic web. It was my PhD thesis. A system that's called DBin, and it's still fun to watch because there's a screencast. So maybe I'll pass you a link in the end. It's an interesting thing. So we thought one of the thinking about peer-to-peer systems back then is that you need peer-to-peer because it's never gonna scale if it's in a single place, right? You had this old idea, and then some guys, Google basically showed us that, well, you could have just a little centralized text box where you could search and you had the entire knowledge of the web, right? So yeah, of course, Google is not like centralized a single machine. It's of course a big cluster, a big cloud of computers. But anyway, they offer a service that goes through a single point, right? So peer-to-peer is not necessarily needed, strictly needed. Academics like peer-to-peer a lot because it makes them publish, because it's very complicated. And they love complicated things. So a lot of people just became professors by writing papers on peer-to-peer. It's true. It's not me saying. But anyway, In 2007, I kind of gave up on this peer-to-peer idea for a number of reasons. Most of all, saying like, look, let's actually see what we can do at centralized level. So what can we do for RDF, for semantic web, at centralized? So taking the technologies that were starting to appear. So for example, Yahoo did this implementation of the Google MapReduce paper, where they were actually introducing the concept of big data, the concept of data-intensive processing. This is not classic supercomputers where basically you have this very expensive machinery which exchange speed of light, for very complex computation. This is computations which might be very simple, might be a regular expression, but it's on a humongous amount of data. And the key there is not to move the data, but bring the computation to the hard drives, because whenever you start reading it, you're dead. So you want to be as close as possible whenever you start hitting the network. So Yahoo had this implementation, which was Hadoop, right, which then became Hadoop open source. That was the early days where this became available, right? So we started to say what we can do with Hadoop, with data-intensive techniques, with NoSQL databases, and with information retrieval. Information retrieval, some of you know Lucene, Solr. What's the difference between Solr, Lucene, and a database, MySQL? Profoundly different. You can both do queries, but they're very, very different if you look at the heart. And information retrieval is immensely scalable. I mean, Google is indeed information retrieval at its best, right? So what can we do with information retrieval on top of RDF? These were the challenges, okay? So basically, our core project up to last August, 9 months ago, has been this one. This is sindice.com. Sindice.com is a very it's a special search engine, because what it does is it throws away all the text. It doesn't care about the text of the web pages. What search engine is that? It only cares about the triples. So we said, well, there is so much work already on processing text and this and that there's no need for research in a sense for that. So we basically throw away all the text, and we only keep the triples. We only keep the annotations. So I think most of you will be probably familiar with this, but just to remind ourselves, what are these triples that we find on the pages, and what is Sindice? So, for example, here you see, let me actually reload it just for, this is the homepage of Sindice. We have the data that just came here. Actually, I think there must be something. So you want to be rich.com, right? And it has 87 triples in each one of those pages. They just came through the crawler. So let's see what triples they have. You can click here, and you can see it will show that the triple just came from the crawler. Well, there's a lot of information. Let's see if we can see how they look like using a graphical representation. It will show you. You could zoom in. So this is a person. These are hyperlinks. So it's kind of a little social network here that they're publishing for each page. Just to give you an idea of the kind of rich content that nowadays you find on the web. Every time you see a like it, you might know it's Open Graph, and Open Graph is a form of annotation. You actually have a rich vocabulary for that. Then last May, Google, Yahoo, Bing come up with this thing, Schema.org, comply or perish. So it's like, you have to add that. The search engine optimization people say that you have to add it because otherwise this and that. So just to give you an idea, we have a little tool here, which some of you might know already. It's the Sindice Inspector. Sindice Inspector, you can find it on the Sindice homepage. Here you have Inspector tool, or you can actually go to the Inspector tool, which is inspector.sindice.com. And it's a nice little tool because you can put in a URL. So this is Rotten Tomato Toy Story. Just to give you an example, this is the page. You get the review about Toy Story, and you see this, there's like it, so you maybe kind of suspect that there is something under it. And there is a little bookmarklet here by which I can just click, and it will go. And now you're going to see what Google sees out of this page, right? Sorry, Google. Sindice sees out of this page. So Google sees less than Sindice unless they're using our library, because we have a library. I will explain you. We have a library called Any23. Any23 you might have heard if you work with web data, because it's an open source Apache project now, Apache Incubator, but it's doing very well. Maybe it will graduate. And it's our stuff. So it came from Sindice, and we open sourced it. Now there was a community of people working on it. But we started it ourselves. We wanted to get microformat, RDF, RDFA, microdata, then all the dialects, the schema, this and that. You always get comma-separated value. It does fixing, it fixes broken markup. So it's a library which is particularly flexible. We developed it ourselves, and now went open source. So this is what you can find in the Toy Story page. just to get you an idea. And it's very rich content. Once again, I mean, this looks like a little bit like the one before, but it's actually even better. I mean, they have the list of actors, they have the full reviews, they have the reviews aggregates, they have the summary of the reviews. So it's very nice data, okay? Now, if you can extract a single page in a correct way, and then you have a correct way of crawling it, which is comprehensive, so it crawls, it kind of guarantees you 100%, right? And a crawling which also guarantees a certain timeliness, so you have a certain delay and you know that you're within that delay, then you basically have like kind of a mirror of a database, right? So you can see a website, not as a collection of text anymore, but really as a database of which you have the records stored, centralized. And if you see it like that, I can tell you that SindiceTech has maybe 5 million databases inside it, because there are 5 million websites which expose markup, and that's more or less what we have inside. So that becomes interesting, because a website you start to see it as a database, effectively, right? So how much it is in SindiceTech, just to give you an idea, this is 647 million documents. These are not documents, they are RDF graphs. So it's 647 million RDF graphs, totaling approximately 80 billion triples at the moment. 80 billion triples, why? Because we also do reasoning on each one of them. We do a specific RDFS reasoning so that the data is actually expanded, so you can think it's about twice as much as we harvest. Okay? The database is approximately, I think, 5 to 6 terabytes at the moment. I haven't checked, but it's a big database. We run all this on our own cluster, approximately 40 machines, but out of 40 machines, we only use like 13 machines for processing, 2-3 machines for the main indexes, and 16 machines for playing around with Virtuoso, basically. Virtuoso is a database. So a ridiculous amount of machines for Sparkle, because it requires this immense amount of hardware. But anyway, what can you do in SindiceTech just to get an idea? Well, you can put here something right to begin with. I can put whatever, the rules, this co-founder of SindiceTech, and you can, you search this and you find 216 documents which are mentioning him. You can then group by dataset, which is actually particularly interesting, because then you start to see things as a dataset. So you see in which website is Renault most mentioned, and you will find, for example, that there it is. So, for example, it's mentioned 26 times in data.semanticweb.org, 25 times on Mixonomy. So you see what it is. So you start seeing, like, if these are data sets. It's kind of like you're looking for data sets in which that concept is contained. You could put, for example, something else, and I can put, like, I don't know, Fiat Punto. It's an Italian car. I don't know if you know it. So you put the name of an Italian car, and it will say, all right, so driveinside.com has 81,000 mentions. Tazit has 2,000. Market.nl Comparis, carsurvey.org mentions 500 times. So it's kind of interesting, because it starts kind of like hinting you at which data sets, because these are data sets at this point, are available, right? And if you have your own website and you're publishing schema.org, you have, for example, your own WordPress, which you have the proper team of this and that, and SindiceTech kind of hits and you have a proper sitemap, so we start harvesting you, then you show up there if you have about cars. So that's cool. It's so open in a sense, right? Your data set, your database becomes part of the vision automatically, just because you're following the standards. So, okay, so you say, well, okay, but that's just a keyword search, right? I mean, it's just, anybody can do that on top of Solr, right? And then say, well, no, we actually went more, because we wanted to be able to do structured query. It's RDF we're querying, so we want to be able to do triple patterns, and that's why we, for example, let me go back to the example where I had the name of a person. There is this advanced search here, this advanced interface. It's a little bit small, sorry guys. Can make it a little bit bigger. But you have this triple pattern concept by which you can, for example, say, oh yeah, it must contain a triple pattern, subject, predicate, object. For example, nose. And if you do this, you actually find only the pages where Renault Gros, and then there is a pattern that says nose. You see? So you can actually search documents that contain certain data pattern. You cannot do this in SWeb. So in order to be able to do this and be able to, this is what I was telling you before. This is extension of information retrieval tools to structured data. Okay? So that's a product, basically a tool, an open source. It's partially open source. The first version is open source. Now we have the new one, which still isn't released. And we don't know if we're going to put it in open source or not, it depends. It's called Siren, Semantic Information Retrieval Engine. Siren, you can actually find the old version from 2 years ago on siren.sindice.com. There's actually, if you know this book, you've seen in action, there's a nice description of what the old Siren does. And I will explain to you what the new Siren does. I have slides about that. Okay? So, we had to invent, in a sense, a technology that would be as scalable as the search engines, as this thing updates every 20 minutes. You can just pump in whatever you want. But that would work on RDF. Another thing that we had to do, and was most important, was to do something useful with this. That's a big challenge. It's semantic data, it's semantic technology. And let me show you.
It's not all just for fun.
Well, I mean, we get money and we get paid anyway. We have great anyway, I never pronounce that word anyway. We never go for pints. No, we do actually on Friday. But anyway, so let's say that you have 80 billion triples, right? And like in SindiceTech, you can say, wow, I have all this information, I can do everything I want. Well, you can't. Why? Because it's so dirty. This triple are half broken, and you can publish RDF and you can validate it with the inspector. A lot of people just don't check it, right? So it's a mess. That doesn't mean that it's useless. It means that before you can actually do something useful, you'll have to do processing. You'll have to actually do a lot of rules. You have to curate it. You have to decide what you want and what you don't want. There's a lot of things. So one of the things that people were asking us, for example, was about consolidation. Say, hey, there's 10 places that they're talking about Fiat Punto, or they're talking about Giovanni Tummarello. Why don't you put in the index a link so that in the end, when you find one, you find everything else. So you can really get like a vision of everything that's said on the semantic web about that person. I don't know, if you guys know RDF, of course you know URIs, right? And in general, people should reuse URIs. That's the dream, right? Because who the hell is going to go and find out what's the right URI for something? It's impossible. So you'd rather be publishing a blank node if I want to use RDF and say, okay, that's my friend Joe, and whatever, he lives here or there. And then, so consolidation is really a fundamental thing. However, so why don't you guys do consolidation? And my answer was because I don't know what kind of consolidation to do. Like, it depends on the application. So if you want to do an application, for example, a search engine, you want something that has recall. Because if there is some noise, the user can spot the noise and just simply disregard it. But the user, will want to see more information. If you're doing something that serves agents, then the agents is not intelligent enough to understand what's noise or not. So you better have some clean information. Maybe you're missing something out, but if you're doing something for a machine, in general, you want some more precision. So every time you do consolidation between entities, you always have a parameter, and you have to set it. It depends on what you want to do. There is no correct, one size fits all. So that was kind of an inspiration to say, look, we don't need a single way of processing it inside SindiceTech. There is no single way, but there is multiple ways by which this data can be processed according to what you need to do. So we started having this concept, this idea of semantic sandboxes. Semantic sandbox it's a data space. We call it also data space where you can process massive amounts of information. I mean, you can think 6 terabytes here, and they can flow the 6 terabytes. They can actually flow across these boxes. Data spaces own resources. That's fundamental for us. So a data space, for example, every time you see one of these, this is like a database. So what kind of database is it? If I could zoom this, you'll see that this one is actually where we put the front end of SindiceTech. So the data comes here, there is some processing, and there is 3 indexes that are loaded in order to serve SindiceTech.com, to create SindiceTech.com. These 3 indexes are Siren, which is the one I was showing you before, that actually does the searches. HBase, which is a key value store, which serves the cache. And also there is a Sparkle endpoint, which I haven't shown you, but and cannot take all the data. It just takes a fraction of the data. Okay, so we have these 3 indexes, and from here we put the front page. But the concept of data spaces, it's actually used to create spaces for a specific purpose. For example, this is just an example. You can say, I want everything about e-commerce, because I want to create an e-commerce application. So please get me all the triples from websites that have something to do with price, right? So you can put a filter and get, from 6 terabytes, it can become 2 terabytes, and they go here. And then you say, well, no, I want to have another one which is more refined, so I'm going to do some consolidation in a particular way, whatever. And you actually create one. And at the end of the e-commerce one, you can say, oh, I want my own refined Siren. So I want to build a new Siren or a new key value store, for example, because that's going to contain the data after being polished. So these data spaces are not just only places where there's a lot of rules and transformation happening, but they're actually ETL-like spaces that basically load a number of indexes. So which indexes do you load? Well, the thing we learned is there's no solution that fits all. You have to load multiple indexes in parallel, denormalizing data for whatever your need is. So, for example, MongoDB is an excellent solution. HBase is fantastic if you just need to do lookups. Siren if you need to search. MySQL if you have certain relationships that will be too big to materialize. So you still need a few tables, but it's very fast once you create the proper indexes. So why not? I mean, in the end of each data space, you actually create the indexes that you need. And the system, the really cool feature that the system has is the fact that these data spaces live in the clouds. But I'll show it to you because this still is kind of Sindice.com. This was an inspiration we had in Sindice because we actually said, look, in order to do something with all this data, we need to create these semantic spaces, okay? And then we'll see later how we did it. So we were actually happy and we were doing this, Sindice.com thingy. And we had no idea how to commercialize it because, yeah, it's cool, it's great, it was working better and better, but we didn't see a use case, okay? Specifically. Then at a certain point we had some people calling us and basically this is a pharmaceutical company, this one is a pharmaceutical one as well. Elsevier is the world largest, probably the world largest, I wouldn't want to say something wrong, but it is either that or very close. What? It's the largest publisher, scientific publisher. It was like 6 billion a year or something. So they came to us, these people and more actually, there's other people. They told us, we've seen this Sindice, so these people are sold on RDF. They like RDF. They don't want to see relational databases, data warehousing traditional way. They don't want to wait 4 months to integrate the databases that the IT department would ask, right? They were sold on the vision. They just couldn't do the scale. So we got a request like, we would like a Sindice for our own company. And we were like, what do you mean we would like a Sindice for our own company? Yeah. We have as many documents as you have, but we want it inside and we want to be able to handle it with this apparent ease that you guys are handling this semantic document. It's RDF. Elsevier was already using RDF inside. They had all the annotations in RDF. But trying to load a simple triple store and not even able to start. Okay? So that got us excited and said, well, you know what, maybe we can make an enterprise offering out of this. Maybe we can extract the pieces from Sindice that actually will allow enterprises to build their own Sindice inside. Not really a search engine, but do whatever they needed with all these cloud spaces and everything that needed. Maybe give you a couple of use cases which are particularly interesting. This is very small text, so just listen to me. This actually text, this write-up comes from one guy in the pharmaceutical company, which is saying the traditional warehousing is not entity-centric. I mean, we have to go through the IT department. It takes a long time. We need to be able to be agile. Let me give you one use case where processing data, for example, from Elsevier can become very valuable once you have this data space, these sandboxes. Imagine pharmaceutical companies. Pharmaceutical companies have what are called product development pipelines. Product development pipeline, you start from like a high throughput experiment that outputs like thousands of molecules, and then you select a few and you go next, and then you try something else, and you go in the labs, and then in the end you have trials, okay? And each one of the steps is incredibly expensive. I mean, it becomes more and more expensive with each step. So what you want to do is fail fast, what everybody says. So discover as soon as possible if a molecule is not going to make it because of some problem. The sooner you discover that, the more money you save. Okay? So anything for them. So and they live in a world where new data sets are available all the time. Because of this open data publishing, there might be some guy in Canada out of a research lab which outputs this database, which is very interesting. And if they had known that X and Y, they would have probably saved time, and they would have probably cut the pipeline earlier. So for them, which we kind of call knowledge-intensive enterprises, these are enterprises for which being able to ingest new data sets becomes like really needed if they want to stay competitive. Not every enterprise is like that, obviously. So just a few. But for them, they just couldn't wait the time for the integration. Imagine, for example, people like Elsevier, we should do publications. So you can ask me, that's a lot of articles. You can read the articles. So what do we do? Why do we need RDF data processing? Well, let me give you an example. I told you about these high throughput experiments that they output 1,000 molecules. What if you could, at very large scale, merge the publications with the annotations from the publications with these results that come out of a machine? So instead, you still have 1,000 results, but you'll be able to rank them and say, you know, this molecule seems very promising because in this article, you know, it says that it refers to the same gene that you're looking at. These other molecules is not good because in this other article, you know, it's mentioned to be toxic or whatever. So you immediately, you know, you could be able to rank these 1,000 results and give a lot of value to the pharmaceutical company because and nobody even read a paper. Nobody even read a single paper. See what I mean? Completely new kind of business model by which content, and they call it smart content, becomes valuable into different enterprises because of large-scale data processing. Okay, so talking a lot here, showing little demos, but you do get some demos in the end. Actually, I showed the signature before, so you should be okay for a few more minutes. Yeah, because you know this seems like yada yada, but we believe it a lot. So this idea, this new kind of data integration, call it. The name is Enterprise Linked Data Clouds. Enterprise Linked Data Clouds. It's a space that it's a strategic knowledge space. It's strategic for the company, and they can actually leverage new data sets in a way that it wasn't possible before. The idea also is integration, pay as you go. What does it mean? Well, semantic technologies, think RDF and Sparkle, right? What is the beauty of Sparkle, like, apparently, is that Sparkle doesn't need a schema. So you get the data sets, and you just throw them inside, and in theory, wow, voila, I can query already. So it's already integrated, right? So all you have to do is just write the proper query. So beautiful, fantastic. That's the best technology ever. Except that doesn't really work, because you can even do integration based on regular expression and strings in Sparkle. You can do that, but good luck in doing a query. You know, it's just going to take forever. It's going to crash. I mean, all sorts of things. So, however, as an exploration tool, it's fantastic. So it makes sense to indeed load a Sparkle endpoint, indeed write your Sparkle query, try to understand what you have and how you could combine it. And when you understand that, go back in the pipeline, put the right rules that says, okay, I'm going to transform this string into that, I'm going to change this into that, so that the data actually becomes much better. And load different indexes, not only Sparkle at that point, that can answer queries at high speed. For example, an HBase, or for example, anything else that at that point you can hit with hundreds of queries per second. So at the beginning, you do get something, you try to understand it, and you refine, and you refine, and you refine. So pay-as-you-go integration. Get some value up front, and then recompute. And cloud computing has a lot to do with this, and I'll show it to you why cloud computing is key. So, this is just to give you an idea. This is kind of like an old diagram, so don't even look at it. It's kind of SindiceTech.com, the data acquisition system, the front end, the messaging queue, the processing in Hadoop, the reasoning parts, etc. But anyway, out of this, we extracted for this enterprise what we call a Sindice suite, which is at the moment 4 elements, which fit together in a way. They look very different, and they do different things, but they fit together by a common theme of this enabling data clouds. The first one is called Cloud Spaces, and it's middleware. And it's the one that implements this sandbox vision. Okay? The very cool thing is that Cloud Space lives in the cloud. So here, the term cloud is used in two ways. On the one hand, it talks about data clouds, and on the other hand, we talked about, it lives in the clouds, so it lives in cloud computing. So there's this little thing about the terminology. In practice, what it is, it's a middleware that encompasses a set of tools, allows you to use this tool in a coherent way, and gives a specific set of APIs, so that that based on cloud layer, which is Amazon, we're using Amazon for Elsevier at the moment. But we're also working with OpenStack. I can't really say that we're running everything on OpenStack because there's still incompatibility, but that's our choice at the moment. On top of this, we put the big data layer processing, so all these pipelines and this ATL is going to do. And on top of this, a set of indexes and a set of systems that you can load in this process, doing transformation using Semantic Web tools. One of these is Siren, this thing that I showed you before. Now I'll tell you a few more about it, but it's not the only one. And by all means, you shouldn't be using Siren if you don't need it. We're not like saying, that's a solution to that. So CloudSpace does this, and I have a little. This is kind of a zoom in into one of the data spaces. So if you take one of those, you can expand it. You will see that the data space owns resources, and these resources are provisioned in the cloud. This is cool because if you provision resources on the fly, you can create multiple copies of the same data space. And you can configure it in a slightly different way, and they all load up at the same time with different parameters, and you can test which one is best. You can make them compete with each other and throw away the one you don't like. So there is basically two main APIs that okay, so you of course you expose this, so you have the native APIs. You have Sparkle, you have whatever you put here. These are the systems that are owned by the data space, okay? But there is also APIs that connect this data space one with another, and they're basically two very simple API. The two of them are, one is differential, so you can have different deltas trickling down the system, and another one is full data. Give me the full data, be that 5 terabytes data, so that you can recompute. And recompute is fundamental. You know why? I'll just go back to this one. Because what happens a lot of time is, okay, so you create a data space based on something before, and then you create another data space based on whatever came before, right? You know what's going to happen most of the time is that you're going to find a bug here that says, we actually should have changed the data here, right? So what do you do now? Cloud computing comes to the rescue. Why? Because what you can do with cloud spaces is say, look, recompute. So it allocates machine on whatever cloud infrastructure it has and creates this new pipeline, basically in parallel, starting from the same data, and reloads this one first, this one next, and the other one. With as many computer as you can do in terms of parallelization, if you can, reloads the whole thing in parallel, and then when it's ready, it uses DNS switching and you go online with the new version. So here you save the day using cloud computing, basically. It will cost you money, but wow. If you had a fixed infrastructure, like a fixed pipeline, how could you do that, right? So this is how a data space is configured. It's just an example, just a mock-up. But basically, you can have an iPhone data space, okay? And the iPhone data space, you can set dependencies and say, I depend on e-commerce data space and price data space. And then you say, look, I own these resources. I want an SQL database, and I want a MySQL, and the name is SQL. I want a Siren, and the name is Index. I want a triple store, and the name is SparkQL. And so it's provisioned. These data stores are provisioned, and they are now owned by the data space. So if you create another one, you can simply say iPhone data space 2. It will create new resources for that, right? And what you get in the end is really a DNS. So you really get something like Sparkle dot iPhone data space dot my data spaces dot your website or something. It really creates a real resources that you can then write an application that uses it. And text to DNS swapping, when you're actually swapping the whole system, you still can use it. So this is a little diagram. It's a little crazy. So I won't really, but this is a little thing that says scale is only one dimension. What I mean is you have scale. You can have a diagram that says, well, this is data model. Data model, you can see it as from less flexible to more flexible. Less flexible being just relational or whatever. Then you have XML, which is a tree, and then you have RDF, which is a full graph and can encompass everything, right? So you have a scalability in terms of data model. Then you have a scalability in terms of scalability, like how big, how much data you can process. Different solutions here that you can place according to which technology you use, right? But then we also argue that there is an extra dimension, which is this ability for you to cope with the unknown data and recompute by using cloud computing. So it becomes kind of an extra dimension that really probably one of those dimensions that we're missing in the picture, probably in the use of large-scale semantic data technologies. Okay, so now at this point, I talked to you about cloud space. Okay, this kind of framework for creating semantic sandboxes. And I'll go back a little bit on Siren. Now, I don't know, because now I have some slides which are specifically talking and discussing Siren and why we think it's very fascinating. I tell you that probably the name, I'm not sure yet, but probably the name is going to be renamed, and it's going to be called Relational Solare, or Solare Relations, because that's what it does, basically. You can materialize relations, and you can query them at the speed of Solare. It doesn't use loops and fors, and there's some hack like that you can use with Solare, but that's a different story completely. This one is the same speed that you expect in a query, just that you can materialize. So you basically can put full JSON-like structures inside each one of the documents, and you can do a full query that asks the path, and you can use any operators, whatever. stemming, whatever sound alike, whatever you want to do on each one of the fields. And you don't have to create specific indexes like you would have in Mongo. So I have a few slides, but I'm going to go very fast because they're pretty technical and tell you the difference. Because some people say, oh, why do I need Siren if Solr already does metadata fields? In Solr, you can already have metadata fields. There are a lot of reasons why, because basically they crumble, they collapse. This is a loading test. This one is the time that it takes to load a semantic database. I think I don't know if it was Sesame or Jena. I don't remember. It was a long time ago. This is just to tell you this is a logarithmic scale that if you load Siren, it's actually incredibly fast and goes to millions and then billions, like that, in a flat way. But you cannot ask Sparkle queries. So I'm not saying, oh, this is so much better than the other. This is different, right? So don't get me wrong. But the point is here that if you don't need the full Sparkle query, so we argue that full Sparkle is great to explore. But once you know what you want to do, you know which API you have to implement at enterprise strength, you're much better off denormalizing and transforming the data so that it fits in something like Siren. If it fits in something like Siren, speed of light, all the enterprise scalability of Solr. So sharding, your replication, whatever you want to do, and instead of being fighting your way through native semantic web APIs. So yes, limitation of Apache Solr, number of attributes, because the way that the Solr works, is basically they explode what's called a dictionary. So if you have two fields like label and name, then the way they actually index it is they do, and they have two names, Renaud-Brew. So label and name are both Renaud-Brew. The way they index it in Solr is label Renaud, label Brew, name Renaud, name Brew. So they basically multiply the number of fields with all the possible values that you can find those fields, and so the dictionary becomes very big until it really explodes. So rule of thumb is maybe a few fields you can have, but you die. This is absolutely not the case in Solr. In Siren, that's a completely different methodology of indexing, so that doesn't apply. There are a lot of things. For example, multi-valued attributes. Multi-valued attributes are very important whenever you're indexing graph-like information. Because what is a multi-valued attribute is like, I know 2 friends, or I have more than 2 friends, I have 10 friends. So those is a multi-valued attribute. The attribute is friend, and the values are all my friends, right? So that one in Solr is somehow supported to a certain degree, but not really. And it's not a bug, it's just the way it's structured. It can't be fixed. So you're actually looking for men friend or something like this. And so basically the way that these are 2 different queries, and you obviously want to find only this record here, because you have men friend here, but here you have men sword enemy friends to no one. So you don't want to find that record. But the way that Solr does it is simply puts everything together so they both show up. But with Siren you don't have this issue. So no full text search and attribute names. Attribute names are the names of the metadata, right? You cannot do full text on the name of metadata on Solr. And because of the way it is, in Siren you can do full text search on the name of the attributes, which is very, very useful. Because imagine that you're integrating like 100 databases, right? And you want to use, you want to put everything in a single index. You want to be able to search, but you will still love to be able to search specifically all the original fields, right, that you had. So if you do this, basically, the name of the field is going to be very important, and being able to tokenize the name, being able to search part of that name becomes very important. So maybe you want, you want to use a very, very rich name where you have database name / table name / column name. So be able to tokenize that and search becomes very important. So in this case, where you're looking for name or label Renaud-Brew, you're going to be finding all this combination because name or label is contained in part of the field name. So it becomes technical, like I said, and the core thing is the ability to index this. But I have a good news. I can show you a killer app for this, which is very visual. So you probably won't see the how it works specifically. It's a bit complex and a bit involved, but it's based on Siren and it's giving you something that wasn't easy to get before. So you'll see Siren in action in a second. A few numbers about Siren. This is how fast we can load it, but actually I don't think this is very relevant because you can go as fast as you want if you actually shard, if you actually have multiple indexes in parallel. You can load them in parallel, you can even merge at the end. So the fact that it was taking 24 hours now, I think it takes 12 in the new version. 12 hours to load 500 million documents. But that's not, you can go actually much faster if you want to. So let me show you another thing that we do in SindiceTech, and that it ties all together at some point with the rest. So I'm not just jumping like crazy, so sorry, it might be several things. So when you have a very large RDF, and especially in general in semantic integration where you want to put all the stuff inside without really knowing what was out there, it becomes very important to have some kind of guidance on what the data was, some kind of analytics, some kind of way of seeing it all together. So we explored this in SindiceTech with Hadoop RDF summaries for data exploration and assisted as part of query editing. It all ties together now in a second, you will see it. Basically, this is SindiceTech. SindiceTech has a bunch of data sets. This is DERI data set, this is DBLP, so this is a data set level. And this is a zoom in. Each one of the data set contains a lot of documents, right? And this document, for example, says that Stefan knows Renault, that Stefan is a person, and Renault has a homepage, etc., etc. And then Renault wrote a paper. The paper is actually referenced in another website. The paper is typed document, blah, blah, okay? So a summary, an RDF summary, is basically a little graph that might be 1,000 to 1 that basically says, it's a statistical graph that basically says people, so person, in general, 90% of the time know other person. And 70% of the time they write a paper, which 30% of the time it's on this website. So it's like a statistical representation, a summary. So you can see like it's an ontology, but it's not. It's really like a data summary. The ontology might be not completely different, but it can be pretty different, okay? Data summaries. Why am I mentioning this? Because, and I actually showed you in action, and this is actually cool. I show you, we do it it takes 12 hours on our computer, on our machines to, oops, my workflow. So, it takes 12 hours to process our data, the full SindiceTech data, but in the end we get this, is a dataset view. So what you see here, you can put the name of any website that we have, right? And it will show you this graph for this website. It's very technical, low level, but so for example, yeah, we have BBC, and this is the information that SindiceTech knows about BBC now. I think this is calculated every week, something like this, I think on weekends. So I'd say, look, BBC has 172,000 pages for a total of 6 million pages, 35 triples per page. And these are the top 20 classes that we see in the dataset, for example, articles. And then you can go here and say for articles, what are the top properties that are used? You can click here and say, well, you have the URL, the title, the image, these are the top properties for each one of those. Okay? And it goes much more in depth, much more in detail. For example, you can go inside this data set and you can go things like, for example, this one, where you can say classes, top relations between URIs and URIs. So we have episodes and genre are linked. Which property links episode and genre? Well, the property category and the property genre is the property that's being used between classes of type episode and genre. So it goes very down in detail. It's really an analysis of the data set at low level. And you know what's like really, really cool if you are semantic web geeks, is that this graph, it's actually RDF itself. So we are materializing all the statistics with our own simple ontology. We are materializing into an RDF graph. Why is it nice? Because this widget, which is very advanced and will show you particular statistics, it's actually, let me show you. You can actually go here, there's this question mark, you can click here, and this is the query that we run in order to get this widget. So it's cool because it is in SindiceTech. You can go there and you have the data and you have the metadata. It's all metadata, right? So you have the metadata there in SindiceTech. And you can even write a query, show me the top 10 first names from people that have something to do with the top classes and top. So you can really do a query that joins cross between the data and the metadata, because it's a join. It's simply a name graph. So it's a name graph like the others. So you can create your own. You can decide your analysis. So this is a very good application of Sparkle and RDF, I think, because the analytic graph, we changed it a lot, because every time you add a new property or something else, and therefore if we use a relational database, it would be crazy to handle. But since we use Sparkle, you just simply change the Sparkle query a bit in case and add the new stuff. Okay, so you calculate these analytics and you say, okay, this is cool. It allows me to understand what's inside the data set a little bit. Then we can also show you things like, for example, crawling statistics. This will tell you how we get it. It's using this kind of site maps. Is it doing this weekly? So this is kind of like showing you the internals of data acquisition so how the data reaches SindiceTech, right? And the data that's inside in SindiceTech, number of pages per day. You get some of this. So these summaries, how do we use this summary? Why they are exciting? And I'll jump to the last two demos, which are basically using these summaries. So one is called the pivot browser, and everything comes together. So this is Siren, this engine, together with the summaries, together with Cloud Spaces, because Cloud Spaces is used to generate these summaries. So you put together the three pieces, and that's what you get, plus a user interface and a specific secret sauce, and you get this pivot browser. And I show it to you in action on a data set, which, okay, so the homepage of the site, the homepage of the company that we started recently, which is trying to bring these things to enterprises, is called SindiceTech, which is indeed, the technology out of SindiceTech that does this. And the idea is enterprise dedicated clouds. So the tool that you need to create this. And so yeah, here you find a little bit of information about the SindiceTech suite, which is these elements that I've shown you. You see Cloud Spaces, you see Siren, and these two things that I'm going to show you right now. But to demonstrate these two things, which are the coming together of this other stuff, I will go to one of the clouds that we host. So we have a life science data cloud. Okay, you click here and you go to a website which is healthcarelifescience.sindicetech.com. This website is a known toy example. So it is an example, right? It is, I think, 5 big data sets, approximately 1 billion triples. So it's not humongous, but it's it's not a toy. And you can go here and see that this data has a certain complexity. You can, for example, zoom out. Each one of these circles here is a class, right? So all the classes in the property. And this is actually, you're using Sparkle on the summary. We calculate the summary of this one. And so at the moment, I think they're actually looking on how much data there is inside. Because there is actually a person that changes this very often. So we wanted something dynamic to show you the content. So this one is also generated. And so on this data set, we are running these two examples. So these two examples work on live data. Okay. First example I'll show you is the pivot browser. There's a screencast, but it's actually easy to also demo yourself. You might be familiar with the concept of faceted browsing. And I think you are absolutely familiar with the concept of faceted browsing. So you have, for example, 1 million entities. This is not a toy. It's 1 million entities. This is 7 million entities, etc. You have 1 million entities, and then you have a set of properties, right? For each one of the entities. And for example, you can say hydrogen bond acceptors, whatever it means. So so I'm clicking here, and when I click here, from 1 million you restrict to 220,000, right? So you restrict the compounds by choosing one of the properties. Okay, this is faceted browsing. You can restrict more, and you will narrow down the list of entities. Now, what Siren and all this that I've shown you allows is something really new, which is the pivoting, which is the relational faceted browsing. What you can do is compounds are tied to assays, which are tied to activities, which are tied to target, which are tied to genes. This is a relational path in the graph, okay? So when I actually restrict this, what it does, it also restricts everything else. Because these, you remember, there were many more. These are only the assays which are connected to a compound which has that property. So at this point, I can rotate here, click on assays, and I will see assays. I see all the properties of assays, and these are only the assays which have this restriction already. Okay? So I can do more. I can click on confidence score and look what happens to activities. Well, activities are immediately restricted. So at this point, I can go to activity. And activity is just the ones that have both the restriction on assays and compounds. Assays and then on compounds that are connected to that. I can restrict more, for example, and look at this. Genes is already 0, so there is no connection. 2 steps away, already it is. And then you can reach here, restrict even more, and look what happens to compounds. It becomes smaller. You can go back to compound, and now you have all the restrictions that you have applied, and you narrow down to compounds based on all these faraway things. I'm sorry that it's compound and assays and things that I really don't understand. It could be people, places they went to school to, funding for the schools, I don't know, whatever. So you can see, well, show me the papers written by people that have gone to schools that are being funded by the state versus, you see, you have this real-time, super relational kind of filtering capabilities, which
I was going to say, and I can add on probably a little more real business context onto this, and that the way that the healthcare field is going towards more targeted therapies. If we can take a look at your genes, we can potentially also find which compounds work better for those particular genes by going to data like this. As there's more research done on patients, and there's just body of knowledge out there that everyone's tapping into.
And we all hope that they do it quick and quicker, right? So we get that service. We get that point when we're going to need it. Nobody's getting any younger. So we're pretty excited about this. We're creating now a new version. It's very easy to create this. So if you have a big data set, all you have to do is, the way we're doing this. Okay?
All right.
Search yourself.
No, I'm fine.
It's all right. Not sure about that.
Yeah,
Well, you might want to
no. Sorry.
Cool.
Gravity works. Thanks.
Okay, so okay, now let me show you another thing. You guys, have you ever tried? Who tried to write this Spark query? Tried to write this Spark query? Not many. Right. So, and let me tell you that maybe who really would like to write the Spark query? They saw Spark and they wish. And who stopped whenever you saw a white rectangle and then he says, write your query here. You feel like you've been cheated because you say, well, it was so easy to load the data, right? And now, can I have my schema back, right? And I see, you don't know. Right? So we had the same problem, and we were like, look, but we have the analytics, we've done the analytics, so we know a lot of this graph, and we can actually support. We can tell you what data is there and what data is not there. So we can tell you what not to write in this part of queries. So I'm actually going to show us screencasts. We have to redo it. It's like boring as it can, but it does show you the thing in action. I hope the audio will be audible, so I'll try.
Hello and welcome to the demonstration of Sparkle, SindiceTech Assistant Sparkle Query Editor. Sparkle is a mature and powerful query language to extract information from intricate empty data sets. The power of Sparkle is well known, but so far its complexity has prevented it from reaching its full potential. Probably the biggest issue that one faces when writing Sparkle
the context, right? So now you say that this is a compound. So whenever you do S, or you have something, it will use the fact that it's a compound and only shows you the property, not only those that are in the ontology, but really those that are in the data that are associated with the compound. So it uses the full context. And it also supports optionals, it supports graphs, etc., etc. So well, you get it. And
Intelligence.
what's sorry?
Intelligence, that's what
Determined for this?
I didn't use it.
Okay, yep. So, okay, and this is based on the analytics that I showed you before. Fine, I am concluding this long presentation, and I know that it's a lot of things, and being told, and yes, please, that shouldn't prevent you from telling me again that it's we should organize the presentations better, as in showing less things maybe, or a little bit more linear, but trying to convey a few messages about this enterprise link data clouds and the fact that we can do things at scale. Now, there's no single solution that does everything. So I'm not advocating the use of a single one. I'm advocating a set of techniques in the end that all together kind of deliver this. To conclude a little bit, what is our status now? We have this big engagement with Elsevier. I share it because it's important for us. And so in Ireland we're okay. We're hiring people. So somebody that's like tremendously interested into this, please talk to me. We're hiring people. We believe that this is a vision that will have a lot of future. So yeah, every enterprise will want one of these. I don't know, whatever. But at least some. There probably is a good section. That's the idea, that we're going to that direction. And we're also very interested in US partners, because a lot of the customers potentially that are interested, the first adopters of this, are clearly big US-based enterprises. It can be pharmaceutical, or it can be other things. It can be defense, it can be all this sort of space. There's so much health data issues. Yes?
So for the Sparkle, it's really cool, do you have a way to split that out, and is that going to be open source at all, or it has to be part of the
So it's nicely split out. There is nicely split out. So there is a version that works purely on top of Sparkle. So you have a Sparkle database, and you connect Sparkle, which is this one. And Sparkle will run a lot of queries, will compute the analytics by using Sparkle. Good luck with that. If the data set is not very big, it will work. And so if it's not, it won't. So if that doesn't work, because you cannot perform the queries in time, then you have to dump all the triples, and you use the MapReduce edition. The MapReduce edition has been tested on 80 billion triples, so don't worry about that.
And is that open source through Sparkle?
So at the moment not, but honestly we're thinking seriously about open sourcing Sparkle, because we think that it just benefits everyone if we get a tool like this, and if there is benefit for everyone, then semantic technologies become more viable, and so it's more business for everyone. So I'm thinking so. Maybe the very large scale one might have some restriction, or maybe it could be like an AGPL license that basically allows everybody to use it, but if you really want to customize and create a different edition, then you should get some license. We'll see. Matter of fact, I'm open to suggestions as well. We're not into, it's just a matter of being able to start a business. So whichever license model allows us the business to exist, it makes sense. Yep. So just to conclude, is we're looking also for US partners. What does partner mean? Well, ideally, we think that we should open an US operation, which would involve technical and also sales. We don't have, so though the company is profitable at this time, we require funding, which we don't have in the sense that we haven't been looking for yet. We're working on creating a business plan and these sort of things. So it might be that in the next 2-3 months we get some funding, and at that point we have enough to start an operation. So whatever. So anyone wants to drop business cards or are interested, we're here. Thank you very much.
Great, thank you everybody. I'm just going to make one announcement. We have on Wednesday LAPHP. We have Semantic Web going to present, and that will be at Factual. So just take a look at the LAPHP meetup for that. Thank you very much, Giovanni and QConnect. really interesting, and see you guys next time.